Welcome back again to the course on convex optimization. A course on convex optimization isn't feasible unless you have some idea about convex sets and convex functions. Now, we had already spoken about convex sets and convex functions in the previous lecture, but let me tell you a bit more detailed study about convex sets, what are their important examples, and convex functions, what are their important examples, what are their important properties, would lead us to understand convex optimization better. Here our aim is not necessarily to give a proof of each and everything that we do, except possibly the major ones, but here our aim is essentially convex optimization and not really convex analysis as per se. And what we are going to do here now is a part of convex analysis. I would begin with by showing you a very important book on this subject. It is called The Fundamentals of Convex Analysis by Carathodory and Lemarechal. This is a book on convex analysis, has beautiful chapters on convex sets and convex functions, possibly one of the best expositions of the subject, and I strongly recommend this book. So, we go back and relearn our notion of a convex set. A set is convex if for any x y which is in the set C and any lambda that you choose between 0 and 1, lambda times y plus 1 minus lambda times x must also belong to the set C. We have given several examples last time, even showing that the human body is not a convex set, and here we would look into from more of the geometrical perspectives and write down some important examples of convex sets. But before that, I will just extend this idea a bit. Let us first define the notion of a convex combination. Convex combination of vectors. Now, consider x1, x2, xk, some k vectors which is given in Rn. So, what you do is the question of, now we are bothering about the question of defining a convex combination. So, a convex combination of these k elements is an element z which is written as lambda 1 x1 plus lambda 2 x2. I am assuming this is known to everyone, vector addition, lambda n xn, sorry, this is again a mistake, it should be lambda k xk with lambda 1 greater than 0, lambda 2 greater than 0, all the lambdas are greater than or equal to 0 and the sum of the lambdas are equal to 1, just like lambda plus 1 minus lambda sums up to 1 and each of the lambdas are greater than or equal to 0 because they are lying between 0 and 1. So, how do you define all possible convex combinations of a set C? You take any collection of finite number of elements from a set, do their convex combination, keep on changing the lambda. So, you will generate new combinations, keep on changing the number of elements that you take from the set. A very fundamental and very basic result about a convex set is the following: every convex sets contains all its convex combinations. Before going into very specific examples of convex sets, and important ones, we would like to state certain specific properties. These properties become important when optimization is handled. So, let us look at certain basic properties, because when you have a set, what are the properties you look for? See, when you have a set, when you have a class of sets, so set of all convex sets, they form a class of sets in Rn, and what you look for is, okay, what happens if I combine two sets, that is if I take the union of two sets. So, if my C1 is a convex set and C2 is a convex set, the question is this convex? You would be obviously sad to know that the very first property that we are considering here turns out to be a negative property, that okay, C1 union C2 is not convex. Let us see. Take a square here, take this square, and take this square in R2. Obviously, I am putting the x axis, y axis for your convenience, but that is really not required. So, this is my C1 and this is my C2. So, this whole set that looks some sort of bit of zigzag, this whole set like this is my C1 union C2, but then this whole set. So, take any point here and any point here and join it, it is outside. Any point here, any point here, the line segment goes outside. So, C1 union C2 is not a convex set. So, if that dissatisfies you, we will give a positive result. What about C1 intersection C2? So, if both of these are convex sets, then this intersection itself is a convex set. Very simple. Again, take this one and take this square. Squares are obvious examples of convex sets. Suppose this is my C1 and this is my C2. So, this is an area which is the intersection, and of course, this is C1 intersection C2, and you can easily see that it is a convex set. I leave you as a homework, those who are listening to the course also have a bit of pen and paper with you, because you need to just figure out something. Everything will not be figured out, because I do not want you to lose out on the fun. So, homework, prove C1 intersection C2 is convex or is a convex set. Let me tell you, any mathematical subject like this fascinating subject like convex analysis or convex optimization cannot be understood unless you do prove things yourself. Proof is an integral part of mathematics, of mathematical discourse, and of mathematical understanding. So, without understanding proofs or without learning to prove things, the fun of a subject is almost lost. So, okay, these are the good properties. Now, I will describe some other property which is essential when you study optimization, is the sum of two sets, assume for us they are convex sets. So, assume C1 and C2 to be convex, and I am asking the question, what do you mean by term sum of two sets C1 plus C2? Now, here you have to realize that C1 is a subset of the vector space Rn and C2 is also a subset of the vector space Rn. So, whenever I am talking about C1 plus C2, the most natural definition is to consider all elements of the form Z such that Z is equal to x plus y, where x belongs to C1 and y belongs to C2. So, this is sometimes called the Minkowski addition of two sets after the famous mathematician Minkowski. I do not want to define C1 minus C2 because you can define it likewise by the difference of two vectors. Critical thing to observe here is twice of C. If you have two sets C, so you can add C plus C, but then twice of C is always a subset of C1 plus C2. Think why? And find an example where this is a proper subset of C1 and C2, and find an example where this is equal to C1 and C2. So, another piece of homework. Two C is proper subset of sorry, not C1 C2, it should be C plus C. Sorry. See, one thing that you can observe, that what is twice C? You are taking the same element and adding them, but C plus C does not mean that you take the same element from C and take the same element from C. It means take just one element from C and take another element from C which could be different to the element that you have chosen before, and then add them. So, find an example where this is a proper subset. So, this homework is find examples. And also find an example where this equals. So, these are the two things that you try to figure out. You will have a lot of fun doing so, just playing around with sets in R2. Now, once I do this, I would also try to define the notion of a cone. Cone is an important class of sets used in optimization, and convex cone is what will be of utmost importance. So, what is a cone? You can understand what is a cone, because if you take an ice cream cone, you call it ice cream cone, that is what it looks like. But in mathematics, this cone is not just, it ends up to the brim of the ice cream, but it it just keeps on extending. You can extend the whole thing in your imagination. And so, cone is a set S such that lambda times x is element of S if lambda is element, if x is element of, if x is element of S and lambda is greater than equal to 0. So, for example, you take an example, take any ray going out of the origin, this is a cone. A pair of rays is a cone, but as you can understand, it is not a convex one, the set is not convex in general. And of course, so any cone which is convex is called a convex cone. This is a cone. So, you can observe, you figure out that this definition what I have given will be satisfied. So, convex cone, not a convex cone. So, this is a very basic thing, and now we go on to some important examples. The first and foremost example, which is very important to optimization, is of the set Rn plus. So, this is a convex set, is a set of all x which is written as x equal to x1 x to xn, but I should write it as a column. So, I give it as a transpose T, where xi is greater than 0 for all I from 1 to n. So, in our setting, this is R2 plus. So, the interesting fact is that this is not only a convex set, important convex set, this is a convex cone. Another important convex set is the space of all symmetric positive definite matrices, is a set of all x element of Sn such that xn such that x is PSD, that is positive semi definite, x is PSD, or in other words you can write it like this with a low n ordering. So, how do you prove that this is a convex set? So, you take one x1 from Sn and another x2 from Sn, in fact Sn plus. Now, what you need to do is to show that lambda x1 plus 1 minus lambda x2 is also in Sn plus. So, you take the lambda of x1 plus 1 minus lambda of x2. In order to show it in Sn plus, we need to show that this matrix is positive semi definite. So, what you do is just take this bilinear product. So, you can write this as W, you must put a bracket to understand that this is a matrix operating on this W, W times lambda x1 into W plus W times 1 minus lambda x2 So, if you look at this, this is nothing but lambda times now, because both of these are in Sn plus. So, both of these are greater than equal to 0 because W is any element in Rn. So, this both of them are greater than equal to 0, lambda is greater than equal to 0 and 1 minus lambda is greater than equal to 0, because to show the convex combination lambda is obviously chosen from 0 1, which is obvious fact, which you need not even state repeatedly. In convex analysis lambda is always between 0 and 1 when unless until mentioned. So, what you see here is this fact that now all of this whole thing is greater than equal to 0. So, okay, let me not write and just put this is greater than equal to 0, implying the fact that Sn plus is convex. We will have more opportunity to talk about Sn plus in the future, and let me talk about another class, important class of sets called affine sets, which are a subclass of convex sets. So, what is an affine set? Affine set, if you take 2 points say in R2, the line segment joining them is a convex set, which I do not have to tell you because the definition simply tells that. Definition of a line segment simply tells that this is a convex set. Now, think of the line which passes through these 2 points. Now, this line itself, if you look at it, is a convex set. Now, it is very important to know that how do I define such a line, or if you have a plane or say a figure like this, a triangular triangle say, but a 2D triangle in 3D, then I can put it on a plane. So, how do I, but that plane is a convex set. So, how do I define such a set? So, such sets like this, like the line passing through 2 points, is a class of convex sets called affine sets, which has the following definition, that a set C is called affine if lambda x1 plus 1 minus lambda x2 is element of C for any x1 and x2 element of C and lambda element of R. Note that lambda no longer has any sign here. So, of course, this is true for any lambda between 0 and 1, signifying that this is also a convex set, but every convex set is not an affine set, because if you take say this set, this, so take 2 points here, take the line passing through them. So, the line passing through them does not remain inside the set C. If this is my set C, the line passing through any 2 points does not remain in the set C. So, this set is not affine, while this convex, this is affine. An important class of affine set is a straight line. So, you can write such straight lines as follows. So, take the set L, say it is a set of all x in Rn, so it is a set of all x which satisfies this equation where A is a member of Rn and B is a member of R. Now, what is important to me at this stage is very simple to prove that this is an affine set just by the properties of the inner product. Now, what is the geometry of this particular type of sets? So, if you look at the R2 geometry for this particular case, if n is 2, then you are basically looking at some line like this. Now, if you look at this line, what is the nature of A, and okay, does A have anything to do with the line itself? Let us take any line point x0 on the line, right. Then what would happen? Then of course, if x0 is element of L, we can call this as linear manifold, that is a more technical term, but forget it. So, if x0 is element of L, then what happens is A of x0 is equal to B. Now, if that happens, then I can replace in this equation B with A of x0, and then I can write L as the set of all x such that A of x minus x0 is equal to B. So, what happens is that if you take this x and take any x here. So, if this is my x0 vector and this is my x vector, then this thing, sorry, just have to rub it. Okay. Now, this is your x vector and this is some x vector, and take any x. So, this vector here is your x minus x0, and what does this equation say is that this A is, sorry, this would be a mistake, A x minus x0 should be equal to 0, because you have put B equal to A x0 and then you transferred it. So, what it says on the x minus x0 vector, so x minus x0 obviously is lying in this plane. You can understand that this vector x minus x0, A is perpendicular to the vector x minus x0, but since x minus x0 lies along the plane from the geometry, so which means that A is perpendicular to the plane itself. So, what does it mean? So, what it shows that A is perpendicular to the plane itself at x minus x naught. That is exactly what is the nature of the element A. So, A is an element. If you look at x minus x naught, just a moment, if you look at x minus x naught, this element is in the orthogonal complement of the vector A, right, is in the orthogonal complement of the vector A naturally. That is what we had just said geometrically. So, which means x is element of x naught So, this is so, but if you take any element which is x naught plus a tilde, right, then of course immediately you will get this. So, x in Rn which satisfies that x is an element of x naught plus a tilde, this sorry a perp which is the orthogonal complement of A. These are terms on linear algebra which you are supposed to know, orthogonal complement of A. So, any x which satisfies this is satisfying this and hence satisfying this, and hence L can also be described like this. So, this is also a convex set, but this is rather an affine set and a very important class of affine set. So, this if you look at this L, what does a straight line do? So, if I call this as Ax equal to B, then this straight line is dividing the plane into two parts. Any point that you take here would satisfy Ax greater than equal to B, because this is equal to B and you move up, the value of it will leave the value of B and become bigger, and you move down it will leave the value of B and become smaller, and so this part is called Ax less than equal to B. So, basically I have divided this line Ax equal to B has divided the plane into two parts which we call HU and this is called HL. This is called the upper half space, is a set of all x in Rn such that Ax is greater than or equal to B. The lower half space HL is given by the set of all x in Rn and L is of course HU intersection HL. So, we have now got a fairly decent amount of explanations about, or fairly decent amount of introduction to convex sets. So, after this we will talk about certain important properties of convex sets and then start describing convex functions. Now, we have shown here that L is HU intersection HL, but of course, as a homework I would ask you to show that HU and HL are convex sets, and by knowing that the intersection of two convex sets is convex, you can immediately deduce that L is a convex set. Now, an important property of convex set is the following, that if you look at the interior of a convex set, if you take a convex set C and look at its interior, I am sure all of you know what is the definition of an interior. In case you do not, look up any standard book on analysis. So, if C is convex, then this set, the interior of C is also a convex set. Similarly, if you look at the closure of a set C, if this is convex, this is the set C itself, if this is convex, then so is the closure. The proof of this is very simple, that is, take a sequence Zn, take a sequence Zn element of C going to element Z in the closure. So, you see whenever you have a Z, you will always have a sequence Zn going to Z, that is the definition. And using this definition, you can actually prove that the closure is also a convex set. So, you take two elements Z1 and Z2 in the closure. Now, what would happen is that you would have Z1n and Z2n, these two sequences where Z1n converges to Z1 and Z2n converges to Z2. So, now you make convex combinations. Now, these are elements in C. So, you make convex combination lambda Z1n plus 1 minus lambda Z2n, where lambda is between 0 and 1. Now, what happens, because these are elements in C, this is also an element in C, this belongs to C. Now, when you take the limit, so of course, you can fix up a lambda, right, and take such sequences. Now, if you fix up the lambda, that is you want lambda Z1 plus lambda Z2. So, you fix up a particular lambda and then take this sequence. Now, if you take the limit, because it is a linear function, so it will immediately give me that this whole thing converges to lambda Z1 plus 1 minus lambda Z2. So, whenever Z1 and Z2, but since this is in C, by the very definition of closure, this is also belonging to the closure of C. So, whenever Z1 and Z2 belongs to the closure, this also belongs to the closure, proving that closure of C is convex. Now, what is important is that how do you prove this to be a convex set? The proof of this relies on a very important property, is called the interiority property of a convex set. I am assuming that this convex set C has an interior. Every convex set C need not have an interior, we will just speak about that. Okay. So, take this set in R2, this whole thing inside and with the boundaries. So, it is a closed convex set. So, you have this part, the white part as the interior of the set. Now, if you take any point in the boundary, say you take x in the boundary and you take y in the interior, and you join them by the straight line. So, any point in x y, take any z from x y such that z is not equal to x, then z must belong to the interior of C. This is a very fundamental result. If you take any z here which is not equal to x, it must be in the interior. This is a very fundamental property, this will be used to prove this and many other things. So, as I told you that every convex set need not have an interior. Okay. How do I support my statement? Let us take an example. In mathematics, it is imperative that if you want to say something does not hold, just give an example, but if you want to say something holds, then you need to have a proof. So, you take the straight line, a line segment, say joining these 2 points x y. So, this line segment is obviously a convex set. So, my question is whether this has an interior. Now, what do you mean by an interior in R2? Remember, x y is viewed as a set in R2. Now, if I take any point here, then by interiority means I have to take a ball. We had already described what is a ball around this point, such that this whole ball should be in x y, but this does not happen. You take any point excepting the points x y, you take any point, it does not happen. So, x y, if you look at the interior, if I say I n t, the interior, this is empty. but then what is not? Is there something we can speak about its interiority? Because if I look at x y from a one dimensional viewpoint, it has an interior. Then how do I speak about some sort of interior of this set x y? This brings us to two important notions, the affine hull and the convex hull. So, keeping in with the tradition of convex analysis and convex optimizers, I will first define what is a convex hull, but affine hull is what would be of help here. You take any set, a non-convex one. Convex hull is the smallest convex set which contains this set C. Now, this is my set C. Now, this set obviously is not convex, which is very clear. Then, but you see, if I take these last two endpoints and join them up, then this new set with this boundary, this new set becomes convex. So, what convex hull is the smallest convex set C containing convex set containing the set C. So, you take any set C like this, you take any convex set containing this set C. Set C is here with this whole thing. This is one convex set, say S, which contains the set C. Similarly, you can take another convex set which contains the set C, and similarly, if you go on, the intersection of all such sets would be finally what we require, the convex hull. So, convex hull, if I have to define it, is the smallest convex set containing C, containing a set C. So, which means if you have a set C, the convex hull of C, which we define as conv S, is a set of all, convex hull of the set C. Convex hull of the set C, which we define as the intersection of all the sets C S, where S is convex and C is a subset of S. But these are only very qualitative things. Is there any way to represent? In mathematics, representation of sets become a very important issue, especially when you do convex things like optimization. These representations help when you are doing the theory and also in computations. So, how do you represent the convex hull of a set, convex hull of a set C? So, I hope you remember at the beginning of the lecture I spoke about convex combinations of a set C. The convex hull of a set C is a collection of all the convex combinations of the set C, right. So, convex hull of a set C consists of all elements Z of the form Z equal to lambda 1 x 1 plus lambda k x k, where x I is element of C for I equal to 1 to k, and lambda I is greater than equal to 0 for all the I, and summation over I lambda I is equal to 1. Now, this k is element of n, that is, this k can vary. So, you can just take any finite number of elements from the set C and make their convex combination, put them aside in one set. The set that will be formed is a convex hull, but you see your k can be changed, and this is a bad factor in the representation, that there are infinite such k's. You can it is very difficult to really visualize such a set. This was this problem was solved by this beautiful result of Carathodory. Carathodory's theorem says that if C is a subset of Rn, then the convex hull of C is a set of all Z such that Z is equal to summation lambda I xi, I is from 1 to n plus 1. Now, he has fixed it up, you just take n plus 1 number of elements with lambda I greater than equal to 0, summation lambda I is equal to 1, I is obviously from 1 to n plus 1 and all the xi's are element of C. Here is a beautiful representation, I do not have to this number k which will arbitrarily change with every z, you take a z, your k will change in general. Here you take a z, your k, this will not change, and this is a very fundamental result in convex analysis. The proof is essentially for a mathematical audience and not really for the audience that we are targeting here. For a proof, you can see any book on good book on linear algebra or any book on convex analysis, or the books which engineer prefer is this one, Introduction to Nonlinear Optimization or Nonlinear Programming by Bazara, Shetty and Sherali. It is a Wiley publication, second edition is 1993 and I think there is also third edition. So, that and chapter 2 has a proof of very simple proof of this fact. So, now what is an affine hull? You can obviously make up the definition very simply. So, the affine hull of a set C is the smallest affine set containing the set C. Now, let us see what is the affine hull of that straight line or the line segment that we had drawn, not really a straight line, line segment. So, the affine hull, the smallest affine set, okay, this whole space R2 is an affine set. So, obviously, it contains this one, and the next affine set, by the very definition of affine set, you can understand in affine set the whole lines have to be in the set, not just line segment. So, this line that is passing through these 2 points x y, that is the affine hull, that is the affine hull of now. Look at this fact that if I take this x point, so point some point z, and I take a ball of radius say delta. Now, even though is not contained in the set x y, this set is C equal to x y, this convex set x y, but if you observe it carefully, the intersection of this ball centered at z of radius delta, its intersection with the affine hull of the set x y or affine hull of C, this is contained in C. So, this if such a point z where this thing happens is called a point of is a relative interior point. So, z is called a relative interior point. Now, here instead of this straight line, if I take this square, so it is a 2-dimensional set, no longer a 1-dimensional set in R2, here it is a 2-dimensional set. If this is my C, what is the relative interior for this, sorry, what is the affine hull? So, affine hull or AF, it is denoted as AFFC, like conv C is convex hull, AFFC is affine hull. The affine hull of the set C in this particular case is nothing but the whole space R2. So, what happens here is the following, is that once your dimension goes down, when you are a lower dimensional set in a embedded in a higher dimensional space, your affine hull is also lower dimensional, and those are the sets where you do not have the interior, but you have something like a relative interior. So, a very important result in convex analysis is the following: every convex set has a relative interior. Set has a non-empty relative interior. So, relative interior is nothing but the collection of all relative interior points. So, this is a very important statement, because if you take any finite full dimensional convex set like a 3-dimensional convex set in R3, then it always has an interior, and this fact is of extreme importance to convex optimization. This is what is called the Slater's constant qualification, which is of extremely fundamental importance to the study of optimality conditions in convex optimization, and because that those optimality conditions are used in algorithms. So, this whole fact takes in a very meaningful role. So, now we have a fair idea about what a convex, what is a convex set, the convex hull, the affine hull, the very basic facts about convex sets. Let me just tell you a fact about convex cone. How would you characterize a convex cone? Let us go back to this whole issue of cone. Now, the convex cone that we have, two important convex cones that we have spoken about is Rn plus and Sn plus. Now, how do you characterize a convex cone? A cone C is convex if and only if, this is the short form of writing if and only if, IFF, if and only if for any x and y in C, x plus y is also in C. Check it out with this. So, this is your homework, too many homeworks today, but you need to figure out these simple things to have a better idea. You take any 2 points in Rn plus, you see this point is also in Rn plus. Here of course, our demonstration, as I have always told you, would be with n equal to 2, and of course, if you take Sn plus. So, if you take two elements x and y with x positive semi definite and y positive semi definite, is a very simple fact or a very simple way to prove that this is also PSD. So, with this basic fact, we stop speaking about convex sets, and in tomorrow's lecture, which would be part 2 of this, we will speak about convex functions. But I warn you that we would really need to talk about convex functions which are extended valued. Of course, you know what is the definition of a convex function, and few an important property that every local minimum is global when you minimize a convex function over a convex set. But we have not yet considered with all importance the notion of convex functions which are extended valued, and we really have to do it, and we have no other choice, because convex functions which naturally arise in optimization are of this nature, and we cannot say no to it. So, with this we stop today's lecture, which was essentially on convex sets with their basic properties, and next lecture would be on convex functions, and we would speak about them in part 2 of this lecture. And part 3, which would again we will come back to convex sets, but it will essentially be a combination of convex sets and convex functions, which is of extremely fundamental thing called separation of convex sets, because as many mathematicians think that optimization theory is a long corollary of separation theorem. Possibly it is, but not Not exactly so. So, we would like to go into on the third lecture, just this is the first part, second part and the third part is on separation of convex sets, in which we will do some proofs. So, thank you very much and good night.